Hello and welcome to the Maths 2 component of the online BSc program on data science and programming. In this video, we are going to talk about directional derivatives. So, we have already seen the notion of partial derivatives. Let's recall first some of the notations that we mentioned in the partial derivatives video. So, unless specifically mentioned otherwise, in this video also a function will mean a scalar valued multivariable function. If A tilde is a point in Rn, then an open ball of radius S R around A tilde is the set consisting of those points such that the distance of the point x from A is less than R. And finally, E1, E2, En is the standard ordered basis in Rn. So, we made use of the standard ordered basis in Rn in order to define the partial derivatives. Let us recall the definition. So, if f of x1, x2, xn is a function defined on some domain D in Rn, the partial derivative of f with respect to the variable xi is the function denoted by f subscript xi or del f del xi. And how do we define it? Del f del xi is the function which is obtained at as limit h tends to 0 f of x tilde plus h times ei. Ei is the ith basis vector in our standard ordered basis minus f of x tilde divided by h. And what did this thing compute? So, the function f of f subscript xi, which is the partial derivative with respect to xi, computes the rate of change of the function f with respect to the variable xi. This is what it computed. So, essentially what we did was we said, well, your function is defined on the entire domain D, but now let us restrict it only on the axis corresponding to xi. So, if for example, it is a function of two variables x and y, when you want to compute this partial derivative function at a point A, you move your say with respect to x. So, you move your x axis parallelly. So, you look at the parallel line to the x axis passing through the point A, you restrict your function to that just that line, and then you see what happens. So, it becomes a function of one variable. You compute the rate of change at that point with respect to what is happening on that line, right. So, you can think of the rate of change of the function x f with respect to xi, so which is the partial derivative. You can think of this as it computes the rate of change of the function f in the direction of the unit vector ei, and ei is showing up in the expression as well. So, this is the rate of change in that direction, meaning on that line. So, which line? The line containing ei, but which is so ei, remember, is a vector, and now we are moving that vector to start from the point A. Okay. So, in the direction of the xi axis. So, so the direction is the direction of the xi axis. So, which means that you are moving this xi axis parallelly so that it passes through your point A tilde. To spell it out explicitly, let us recall that we can write this expression as limit h tends to 0 f of x1, x2 all the way up to xi minus 1, then xi plus h, and then so one can think of this as xi plus h times 1, and then xi plus 1 all the way till xn, and then minus f of x1, x2, xn divided by h. So, the only change happens in the ith coordinate, all the other coordinates remain the same. This is how this function is, and we can rewrite this as f of, so this part we can rewrite as f of x1 plus h times 0, x2 plus h times 0 and so on, xi minus 1 plus h times 0, xi plus h times 1, and then xi plus 1 plus h times 0, and then all the way up to xn plus h times 0. That is what this is. That is how we get this expression f of x1, x2, xi minus 1, xi plus h, xi plus 1, xn, right. So, now we can ask, instead of thinking about the rate of change in the direction of one of the axis, What if I want to think of the rate of change in some other direction? Yeah, after all there are many directions, right. In the xy plane, well, you have the x axis, you have the y axis, and then there are all these other directions. So, you could ask what about the rate of change in one of those directions. Okay, so, let us talk about the rate of change at a point in a particular direction. So, let f of x1 x2 xn be a function defined in the domain D in Rn containing a point A tilde and an open ball around it. Suppose instead of the direction of the axis, we are interested in the rate of change of the function in some other direction. Okay. So, we can use the same idea as we have for partial derivatives. So, we choose a unit vector. So, remember that we had chosen the vectors E1, E2, En. These are, remember that these are unit vectors. So, these have what we call norm 1. Yeah, recall this from the linear algebra part. So, these have norm 1 or these have length 1. So, instead of E1, E2, En, if you have some other direction, not a direction of for the axis, then we can take a unit vector in that direction, and then we can compute this number limit h tends to 0 f of a tilde plus h times u minus f of a tilde divided by h. So, when we want the direction to be the direction of the axis, that time we use EIs. If it is some other direction, you choose a unit vector in that direction, and then you do the same thing that you did earlier. And if you agree that what the previous expression computed the rate of change in the direction of the axis, so on the lines parallel to the axis, then this will compute the rate of change in the direction of the line passing through this vector u. So, you take that line passing the vector u, move it parallelly so that it passes through A, that will give you some line passing through A and in the direction of the vector u, and then you restrict your function to that line. So, it becomes a function of one variable, and then we know how to compute the derivative. That is what this is. So, to spell this out explicitly, what we are saying is, if a tilde is a1, a2, an, those are the coordinates of a tilde, u has coordinates u1, u2, un, then this, what is this expression? This expression is exactly limit h tends to 0 f of a1 plus h times u1, a2 plus h times u2, all the way up to an plus h times un minus f of a1, a2, an divided by h, and you are taking the limit as h tends to 0. So, you think of this this entire thing as a function of h, and you take its limit. So, how is this a function of one variable? So, you think of g of h as this f of a1 plus h u1 all the way up to an plus h u1, right. And then what this translates to is, this translates to a limit h tends to 0 g of h minus g of 0 divided by h. So, this is exactly the derivative of this function g at 0. So, this is the rate of change in that direction as a result. Okay, so, this is the same idea that we saw for partial derivatives. Fine, let us do a couple of examples to be clear about what we are saying. So, let us find the rate of change of f of x y, which is x plus y at 0 0 in the direction of the y is equal to x line. So, we will apply the definition. So, first of all we need to understand what is the unit vector. So, for y is equal to x, the unit vector you can check is 1 by root 2 comma 1 by root 2. So, if you prefer in terms of angles, the y is equal to x line makes an angle 45 degrees with respect to the x axis, and so unit vector is going to be cosine 45 sin 45. So, this is exactly what we have. Okay, so, now what we want to compute is limit h tends to 0 f of 0 plus h times 1 by root 2 comma 0 plus h times 1 by root 2 minus f of 0 0 divided by h. Okay, so, let us evaluate what this is. So, this is f of h by root 2 comma h by root 2, which is h by root 2 plus h by root 2 minus 0 plus 0 divided by h. So, this is 2 times h by root 2. So, that is root 2 times h in the numerator divided by h, which is exactly root 2. So, that is the rate of change of this function in the direction of the y is equal to x line. Fine. Let's now do the second one. So, this is not at the origin. So, the rate of change of f of x y z, which is x y plus y z plus z x at 1 2 3 in the direction of the vector 4 3 0. Okay. So, now this vector is given to us, but this is not a unit vector. So, we have to first convert it into a unit vector. So, let us see what the unit vector here is. So, if we call this vector v, so as we know, unit vector in the same direction is given by dividing by its norm. So, dividing by its length. So, if we do that, we get 4 comma 3 comma 0 divided by norm of v. So, let us compute what is norm of v. So, norm of v is square root of 4 squared plus 3 squared plus 0 squared. Okay, this is very conveniently 16 plus 9, which is 25. So, root of 25, which is 5. So, this is 1 by 5 times 4 comma 3 comma 0, right. So, this is the unit vector u. So, now what do we have to compute? We want to compute limit h tends to 0 f of 1 plus h times 4 by 5, 2 plus h times 3 by 5 and 3 plus h times 0 by 5 minus f of 1 2 3 divided by h. Okay, let us evaluate what this is. So, limit h tends to 0. So, if you substitute these 1 plus h 4h by 5, 2 plus 3h by 5 and 3 into this expression, and also substitute 1 2 3 in this expression, you will see there is a fair amount of cancellation, and so the terms that are left are going to be h squared times 12 by 25 plus 2 times h times 4 by 5 plus 1 times h times 3 by 5. So, this is coming from your first x y term, this is the expression, and then for the other two terms you probably have only one term each. So, 3 times h times 3 by 5 plus 3 times h times 4 by 5, right, and the other terms cancel with f of 1 comma 2 comma 3. So, I will suggest that you do this. So, and then divided by h. Fine. So, what do we get? So, the h cancels from the numerator and the denominator, and then in the numerator the first term you have an h squared. So, that limit will be 0 and the others will survive. So, what you will get is 2 times 4 by 5. So, 8 by 5 plus 3 by 5 plus 9 by 5 plus 12 by 5, okay, and that is what the answer is. So, the answer is going to be 8 plus 3 11 plus 9 20 plus 12 32 by 5. So, this is what the answer will be. Okay. So, I hope this was a slightly more tedious calculation, but not difficult at all. I will suggest if you did not follow it as I was doing it, please do it yourself. Okay. And finally, here is an example where we specify the direction. So, the direction is 60 degrees from the x axis. So, this is on the xy plane. So, let us see what is u here. So, u here is going to be, so if the angle is theta, then u will be cosine theta sin theta. So, here you have cosine of 60 sine of 60. So, if I remember my sines and cosines correctly, this is half and root 3 by 2, and okay, so now we can plug this in and see what we get. So, the limit h tends to 0, f of 1 plus h times half, comma 0 plus root 3 by 2 times, so h times root 3 by 2 minus f of 1 comma 0 divided by h. So, what is that? Limit h tends to 0, sine of 1 plus h by 2 times 0 plus plus root 3 by 2 times h minus sine of 1 comma 0 divided by h. Okay, so now we can use our trigonometric formula and expand this and get the answer. And yeah, so maybe an easier way of doing this is to actually use the function g that we defined. So here g of h is sine of, so sine of this guy 1 plus h root h by 2 root 3 by 2 h, and what this thing is really g prime at 0, right. So, let us evaluate what is g prime of h here. So, here if we evaluate g prime of h, we get, so g prime of h is cosine of the same thing multiplied by 1 plus, so root 3 by 2 h times this is 1 plus h by 2, so times half plus 1 plus h by 2 times root 3 by 2, right. This is using the composition rule. Okay, and so now if I want g prime of 0, this is going to be I substitute h is 0 in this expression. So, cosine of this same thing. So, 1 plus 0 by 2 times root 3 by 2 times 0. So, that gives us just cosine of 0, and then times, when I substitute here, the first term does not contribute because h is 0, and the second term contributes say root 3 by 2. So, cosine of 0 times root 3 by 2. So, that is just root 3 by 2. Okay. So, that is the rate of change of this function in the direction of 60 degrees from the x axis. Okay. So, I hope it is clear how we are computing this, and that these limits are tedious, but not difficult. Okay. So, let us look at the graphical representation of some of these examples in GeoGebra and try to see what the directional derivative at these points is computing for us. So, let us look at the first example, which was f of x y is x plus y. So, here is the graph of f of x y is x plus y. So, the red line is the x axis, the green line is the y axis, and here is how that graph looks like. So, it is a plane, as we have seen before as well, and we want to look at the line y is equal to x on the xy plane and look at the corresponding plane on top, and then once we intersect the graph with that plane, that will tell us how the function behaves or looks like above that line. So, here is the line y equal to x extended into the plane above it. So, that this is the intersection of two planes, and so if we intersect them, we get this line. So, if I remove the graph and the plane, here is how here's how the picture looks like. So, just I will once again draw the plane. So, here is the plane on which that line is, and once I remove it, this is how the graph of the function on the line or above the line y is equal to x looks like. So, so what is the directional derivative telling us? It is telling us the slope of this line, right. So, if you take the angle of this line with the line y is equal to x, it is telling us something about the angle there. So, tan of that angle, that is exactly what the directional derivative is computing, and you can try and compute it and see that what we have done is exactly that computation. Okay. Let us look at the other example in 3 dimensions, which was the function sine of x y. So, here is how the function sine of x y looks like. So, we have seen this function before. So, this is a very beautiful looking function, and now we wanted to look at the point 1 comma 0, and we computed the directional derivative at that point with in the direction where the angle made was 60 degrees with the x axis. So, if you compute the equation of that line, it will give you this line here, and then we want to look at the plane above that, right. So, that is the plane above that, and when we intersect these two, that is exactly what happens on that above that line. So, above that line, that is what happens. So, here is what happens if we intersect those two, and if I now remove the graph, you can see this is what it looks like. So, this is like the sine function, except that the oscillations keep getting faster as you move away from the axis, as the x or the y values increase in magnitude, as you would expect. So, we want to compute the question that we had, or the thing that we computed was what happens at 1 comma 0. So, this is the point 1 comma 0 over here, and you can see that at that point this is how that curve looks like, and what we are computing is the if you draw the derivative at that point, the slope of the derivative with respect to this line that we just so on that plane. So, that we just erased. So, on this plane, what is the slope of that line, and that is exactly what the directional derivative computes. Fine. So, let us now define what is the directional derivative. So, this is exactly on the same lines as we did for the partial derivative. So, let f of x 1 x 2 x n be a function defined in the domain D in R n. The directional derivative of f in the direction of the unit vector u is the function. So, earlier we were computing limits at a particular point, now we do it as the point varies. So, this is the function, and the important part here is the notation. So, the notation is f subscript u. So, earlier we had f subscript x I. So, here instead we have f subscript u, where what is u? It is that unit vector in whose direction we are computing this directional derivative. So, f subscript u, and the definition is exactly the same. So, instead of a tilde, because we are treating it as a function, we do this at x tilde, and the domain of this function is exactly those points of D at which the limit exists. So, if the limit does not exist, we do not talk about directional derivatives at that point, and if the limit exists, you define the function over there. So, I just want to make a small remark here, but an important one. So, if you take the unit vector E I, right. So, you can define the directional derivative in the direction of the unit vector E I, that is exactly our partial derivative. This is exactly our partial derivative. So, this is a general version of the partial derivative. Okay. So, let us quickly go through some properties. We saw this in examples when we did the partial derivatives, but these hold generally for directional derivatives, and let us put them down clearly. So, one is linearity. So, if you have a constant c and you have two functions for which the directional derivative at a point a in the direction of the unit vector u exists, then it also exists for the function c f plus g, and to compute it you can just do linearity, which means c f plus g, the directional derivative is c times the directional derivative of f plus the directional derivative of g. Remember that u has to be the same, you can't choose different directions and hope to get the same thing, right. Okay, so that is linearity. So, in particular it follows from here that if you have f plus g, then the directional derivative is the sum of the directional derivatives. If you have f minus g, it is the difference, and if you just multiply by a constant, that constant comes out. Then we have the product rule. We did all these for derivatives, and now we are repeating these for directional derivatives. When I say derivatives, I mean from one variable calculus. Okay, so if the directional derivative at the point A in the direction of the unit vector u exists for both the functions f and g, then it also exists for the product, and it is given by the product rule, exactly the same as we had for one variable calculus. So, f times g directional derivative at u in the direction of the unit vector u is f in the directional derivative of f in the direction u at a times g of a plus f of a times the directional derivative of g in the direction of u at a. Okay, and finally, we have the quotient rule. So, again with the same hypothesis, but here we need that the denominator g at a is not 0. In that case, the directional derivative at a in the direction of the unit vector u also exists, and it is given by this formula. Directional derivative of f in the direction u at a times g of a minus f of a times g directional derivative of g in the direction of the unit vector u evaluated at a divided by g of a squared. So, we have seen the exact same formulae in one variable calculus. Okay, so these are useful properties, and they will help us evaluate. Let us do a couple of directional derivatives for arbitrary directions. I am going to assume an arbitrary vector. So, here u is u1, u2, and let us compute what happens. So, limit h tends to 0. So, I want f of f u x y. So, this is f of x plus h times u1 y plus h times u2 minus f of x y divided by h. So, limit h tends to 0, x plus h times u1 plus y plus h times u2 minus x plus y divided by h. And the x and the y cancel out. So, we are left with h times u1 plus h times u2 divided by h, which is u1 plus u2. And I will remind you that in the video on partial derivatives, we computed that the partial derivative of this function with respect to both x and y was 1 and 1 respectively, and I can write this as u1 times 1 plus u2 times 1. For some strange reason, I am going to do that. Okay. So, how about this? This is probably much more complicated. So, here our unit vector is u1, u2, u3. So, if I try to compute this, what I will get is x plus h times u1 times y plus h times u2 plus y plus h times u2 times z plus h times u3 plus z plus h times u3 times x plus h times u1 minus x y plus y z plus z x. This is the numerator divided by h. So, now if I cancel out all the terms only in x, y and z, which does happen because of the term on the right that you are subtracting out, what we are left with is all these terms with the h's, and then there's some h squared terms. So, when you divide by h, okay, so let us write that down. So, h squared times u1 u2 plus u2 u3 plus u3 u1, and then plus h times u1 times y plus x times u2 plus u3 times y plus z times u2 plus z times u1 plus x times u3. Okay, so you can check this is what you get, then divide that by h, take the limit as h tends to 0, and then what we have here is whatever you have in the bracket here. So, this is u1 y plus u2x plus u3y plus u2z plus u1z plus u3x, and if I rewrite that, I get u1 times y plus z plus u2 times x plus z plus u3 times x plus y. Okay, and I will ask you to go back and check what were the partial derivatives of for this function, or you can check it right away. Okay, and see if these terms are these terms here, whether these are things you can identify. Okay. Finally, let us come to sine of x y. This is probably the expression is going to get too messy, so I won't be able to complete this. So, sine of x plus h times u1 times y plus h times u2 minus sine of x y divided by h. Okay, so I have to use my trigonometry. So, this is sine of x y times cosine of some huge thing. So, x times h u2 plus y times h u1 plus h squared times u1 u2 minus plus cosine of x y times sine of the same thing that I have here in the cos. So, this thing comes here, and then minus sine x y divided by h. Okay, so, this is a limit that I claim is totally doable. You have solved limits of this type. So, I will suggest that you sit down and work this limit out and see what you get, and once you can write down that limit, check out what that limit is and what the partial derivatives for this function are and what relation they have. Fine. So, I will end with this example of f of x y is x y by x squared plus y squared if x y is not the origin and x y is 0 if x y is 0 0, and I want to compute the directional derivative at 0 0 specifically. For the other points, it is a tedious calculation, but doable, but at 0 0 there is something specific that we want to see in the direction of the unit vector u. Okay, so what do I have? By definition, this is limit h tends to 0, f of 0 plus h times u1 comma 0 plus h times u2 minus f of 0 0 divided by h. Well, let us substitute in the values. So, this is f of h u1 comma h u2 minus f of 0 0, which is 0. So, I will drop this divided by h. So, this is limit h tends to 0 h times u1 h times u2 divided by h squared u1 squared plus h squared u2 squared the whole thing divided by h. Okay, so if we know how quotients work, you will be able to see that this is just h u1 u2 divided by h times h squared u1 squared plus h squared u2 squared sorry, there is an h squared here. So, this is h squared u1 u2 divided by h times h times h squared u1 squared plus h squared u2 squared. So, the h squared cancels with h squared from the denominator, and what this gives us is that you have u1 u2 divided by h times u1 squared plus u2 squared. This is actually a unit vector. So, the denominator u1 squared plus u2 squared is 1, although that is irrelevant for what is coming. So, this is u1 u2 divided by h. Okay. So, this is what you get, and now u1 and u2 are of course fixed, meaning they have nothing to do with h, and in the denominator you have an h, which means that this limit does not exist, right. So, the directional derivative in the direction u does not exist unless of course one of u1 or u2 is 0, assuming both u1 and u2 are not 0. What happens if one of them is 0? Well, that is exactly the case where you have the partial derivatives, and we checked in the partial derivatives video that the partial derivatives are both actually 0. So, the partial derivatives here do exist, both of them are 0, but other than the partial derivatives no other directional derivative exists. So, the only directions where the rate of change is defined is in the direction of the x axis or the y axis. For no other direction is it defined. Okay. So, in this video we have seen the notion of the directional derivative. This is a generalization of the partial derivative, where you compute the rate of change for any direction instead of just the directions parallel to the x axis or the y axis. You compute it in any direction. The definition is almost analogous, and the calculations are slightly more tedious, although when we saw examples we saw that there was something interesting happening. So, there is some background here, and there is a phenomenon that we have to uncover. That this phenomenon unfortunately depends, as we saw based on the last example, on some conditions. So, we have to talk about something called continuity. So, once we talk about continuity, we will come back and we will show an easy way of computing the directional derivatives once we know what are the partial derivatives. Thank you.